Hello everyone, welcome to Equal To, and this is the 6th video of our Matter in Our Surroundings playlist. If you haven't watched the past 5 videos, I'll give you a link here, you can go and check it out. Now, in this video we are going to see the effects of temperature in the state of matter. Okay, so the question is, can matter actually change its state? Okay, we'll start this episode with a small activity. So you have a beaker and you place some ice cubes into it, and you are placing this above a burner, right? You are placing a burner under this beaker, and you are going to set up this in such a way that you have a thermometer inserted into this beaker, and the bulb of this thermometer, it is immersed into ice. Okay, so that you are going to check the temperature of this ice, right? We also need a glass stirrer that is inserted into it. Now what we are going to do is that we are going to turn the burner on and heat this beaker, right? This beaker with ice, we are going to heat it. Now what will be the changes that you are going to observe? You have to keep a very keen eye on the thermometer, right? Now when you start heating this, obviously you will know that ice becomes water, right? Even when you leave ice in room temperature, it obviously becomes water. When you start heating it, obviously the process is going to be faster, right? So ice is going to transform into water. So it's obviously going to change its state, right? But the thing is that you are going to observe the thermometer, that is the temperature at which the ice cubes are going to turn into water. So if we observe this, what you are going to see is that you are going to turn the burner on, so the heat is on. Okay, so the ice will start to melt. The ice uses this heat and it starts to melt. Now what you would think is that the thermometer should show some change in temperature, right? But it wouldn't show. Okay, up until every single bit of ice is melted, the thermometer will still show the same temperature it started with. Only after every ice cube melts, the thermometer or the temperature of this content would increase. Now why is this? So the thing is that when you start heating, the temperature should increase, right? Or the heat energy, it increases the kinetic energy. Okay, so what happens is that all the heat that you provide, it is used to overcome the forces of attraction between the particles of ice, right? Ice is obviously solid, so it would have higher force of attraction between the particles of ice, right? And you are going to convert it into water. Water obviously has lower force of attraction between its particles when compared to ice. So to overcome this force of attraction, you need energy, right? So the heat that you provide using the burner to this ice, it is used to overcome the force of attraction between it, and it is not used to heat up, right? The temperature doesn't increase. Okay, it is just going to use it to overcome the force of attraction. Okay, this is what happens. As the temperature increases, obviously kinetic energy increases, so the ice cubes, they are converted into water obviously, but actually the heat is used to overcome the force of attraction, so you wouldn't change you wouldn't see any difference in the thermometer reading, and it would change later, right? After it melts, it would start changing. Okay, now coming to important term called melting point. Okay, so what exactly is melting point? I'll first tell you the textbook definition of it, and later we'll explain how it is. Okay, the minimum temperature at which solid melts to become a liquid at atmospheric pressure is called the melting point of that solid. Okay, so what are they trying to tell? A solid on heating would obviously convert into liquid, right? And that temperature at which it starts converting, that is what they call melting point. And there is one important term that you have to mention for sure in your definition is that atmospheric pressure. It's the standard temperature or pressure, standard pressure, right? Because the state of matter will also depend on pressure. We'll see that in the later part of this chapter, but for the definition's sake, you have to remember that melting point is the temperature at which the solid is converted into liquid under standard conditions, under atmospheric pressure, under normal pressure, right? So that is melting point. So you start heating your beaker filled with ice, and at some temperature it converts into liquid, right? It converts into water. That would be the melting point of ice. Okay, so that is the definition. And basically melting point, it shows the strength of force of attraction. Okay, obviously solids have high force of attraction between those particles, and higher the melting point means that the strength is very high, because as we have seen, the heat that you give, it is used to overcome the force of attraction between these particles, right? So higher the melting point, more force of attraction is present. So more heat or more energy is used up to free up these particles to become liquid. Okay, that is what they are telling here. Now, one more definition is fusion. Okay, the process of converting solid into liquid by applying heat is what we call fusion, right? In this example, we saw that we are heating ice and it becomes liquid, right? It becomes water, and this process is what we call fusion. And the melting point of ice is 273.15 Kelvin. Okay, we earlier saw what melting point is, right? It is the minimum temperature at which a solid melts to become a liquid at atmospheric pressure. That is what we call melting point. So the melting point of ice is 273.15 Kelvin. At 273.15 Kelvin temperature, ice becomes liquid, ice becomes water, and this process of conversion is what we call fusion. Okay, now we have one question. We measured this temperature in Kelvin, right? So what exactly is Kelvin? Kelvin is the standard unit, SI unit of measurement of temperature. Okay, to make it easy, we call 0 degree as 273.15 Kelvin. Okay, 273.15 Kelvin is the melting point of water, right? We have just seen it, and that is what we call 0 degree Celsius. Okay, we are basing the entire concept of Celsius on the melting point of ice. Okay, we are using melting point of ice as the reference to create this Celsius unit. Okay, Celsius is not SI unit, Kelvin is SI unit. We will be mostly using Kelvin, but in our day-to-day life we use Celsius, right? So here is the conversion. 0 degree Celsius is 273.15 Kelvin, and 273.15 Kelvin is the melting point of ice. For convenience sake, we have rounded it off to 273. Now for conversion, how would you do? We know that 0 degree Celsius is 273 Kelvin. Okay, so to convert Kelvin scale to Celsius scale, we subtract 273 from it, and to convert Celsius scale to Kelvin scale, we add 273 to it. Okay, this is something that we use to solve problems. We are probably doing it in the exercise later. You just have to remember that Kelvin is the SI unit of temperature, and the melting point of ice is 273.15 Kelvin, and rounding it off we get 273 Kelvin, and we use that as 0 degree Celsius because for convenience, right? Now we introduce a new terminology called latent heat. Okay, the actual meaning of latent is hidden. So what is the definition of latent heat? Latent heat is the heat that is used to overcome the force of attraction between the particles. Okay, now when we heat the ice cubes, the temperature didn't actually increase, right? But the ice cubes were converting to liquid, so the heat went somewhere, but it didn't increase the temperature. So the heat is hidden, right? you are not actually seeing the temperature increase by supplying the heat. So the heat is hidden, and that is what they call latent heat. Heat overcomes the force of attraction between these particles, right? That heat is what we call latent heat. Latent meaning hidden. I hope this is clear. The heat used to overcome the force of attraction between the particles. Now one more term which is very close to this but slightly different is called latent heat of fusion. Okay, we have already seen two terms. One is latent heat, which is what which is the term used to mention the heat that is used to overcome the force of attraction. The other one is fusion. What is fusion? Fusion is the process of converting solid to liquid, right? Now latent heat of fusion is just a combination of these two things. I'll just read this definition once and I'll explain. You will understand this very well. It's quite easy. The amount of heat energy that is required to change 1 kilogram of solid into liquid at atmospheric pressure at its melting point is known as the latent heat of fusion. I know it's a mouthful, but let me just break it up to you. Okay, the amount of heat energy required to change 1 kilogram of solid into liquid. Okay, so fusion is converting solid into liquid, and latent heat is the hidden heat. Okay, so the hidden heat, that is hidden energy, that is used to convert 1 kg, we are standardizing things here, 1 kg of solid into liquid at atmospheric pressure. Another term that is used to standardize, right? 1 kg and atmospheric pressure. At these conditions you are converting solid into liquid, okay, at its melting point, because only at its melting point it would start converting, right? Only at its melting point it would start converting to liquid. Only at its melting point ice will start converting to water, right? So at its melting point at atmospheric pressure, the amount of heat that is required to convert 1 kg of solid into liquid, or in this case you could say 1 kg of ice into water, that would be the latent heat of fusion for ice, right? At atmospheric pressure, at the melting point, at that temperature, what is the melting point? 273.15 Kelvin. You can round it off, just 273 Kelvin. At 273 Kelvin at atmospheric pressure, the amount of heat required to convert 1 kg of ice into water is what we call latent heat of fusion of water. Okay, this is the definition. So you know what latent heat is, the hidden heat. You know what fusion is, the process of converting solid to liquid. Okay, and now you know what latent heat of fusion is, right? It's just a combination of these two things. So I think you got it, right? This is one thing that has been asked a lot of times in board exams. Okay, coming to the next definition. I know a lot of definitions are involved in this particular session, but I hope you understood this well, and these are quite easy things, but these are important. They would be mostly asked in your exams, right? So coming to boiling point. What is boiling point? Let me first read out the definition and I will explain it to you then. The temperature at which liquid starts boiling at atmospheric pressure is known as its boiling point. Okay, I think you would probably be confused by the definition, because the definition of boiling point contains the word boiling. So what exactly is boiling? Okay, it's not quite difficult. When you start heating water, at some point you would see that the water starts bouncing, right? It gets very bouncy. It would probably have a lot of bubbles. That is the boiling, right? I know you're quite aware of boiling. Like it's the same thing. It's nothing complex. The temperature at which a liquid starts boiling at atmospheric pressure. Like whenever you are going to define some temperature or some point or something like that, you have to mention the conditions at which you are defining it, right? Mostly you are required to use the term atmospheric pressure, right? It's very important. it's your definition is worthless without this point. Okay, the temperature at which liquid starts boiling at the atmospheric pressure is known as its boiling point. Okay, at atmospheric pressure, the temperature at which liquid starts boiling. So for water, this temperature is 373 Kelvin. You know that melting point of ice is 273 Kelvin, right? So the temperature at which the solid ice becomes liquid water. Now boiling point is when the liquid water gets vaporized into water vapor. Okay, and that temperature is 373 Kelvin, exactly 100 degrees away or 100 units away, right? So when you convert this to Celsius, it would be 100 degrees Celsius, because we know, right, we are going when you are converting from Kelvin to Celsius, you are going to subtract 273. So 373 minus 273 gives you 100 degrees Celsius. So at 100 degrees Celsius, water starts converting into water vapor under atmospheric pressure. Okay, so this is the boiling point of water. I hope you are clear with the concept of boiling point. Now there is one more thing that is highlighted here, that is called as bulk phenomenon. Okay, so what exactly is bulk phenomenon? At boiling point, a lot of these molecules, a lot of these particles gain energy simultaneously, and they starts vibrating rapidly, and it starts vaporizing immediately, right? It doesn't happen one by one, it doesn't happen particle by particle, it happens instantaneously to a lot of particles, to the bulk of water molecules, right? That is why they call this a bulk phenomenon. Okay, so I hope you got what boiling point is. Moving on, we have another definition, latent heat of vaporization. We saw melting point, and something that came after that was latent heat of fusion, right? Melting is fusion. Basically melting is fusion, right? Because solid to liquid conversion. And we just saw boiling point, in which it vaporizes liquid into gas, and then comes latent heat of vaporization. So I hope you would be able to tell the definition of latent heat of vaporization with the definition of latent heat of fusion, right? In latent heat of fusion, what did we see? 1 kg atmospheric pressure, energy used to convert solid to liquid, right? The same applies for latent heat of vaporization. 1 kg atmospheric pressure, but the thing is that instead of fusion you have vaporization, right? The heat required to convert 1 kg of liquid into gas instead of solid into liquid, right? That is the only change here. The amount of heat required to change 1 kg of liquid into gas at atmospheric pressure at its boiling point. Okay, there it was its melting point. Here it is its boiling point, is known as latent heat of vaporization. So this is one more definition, and I hope it's quite clear. You can tell it by yourself. Now you would have observed that solid on heating becomes liquid, liquid on heating becomes gaseous state. Okay, and why is that? The heat that you provide, it is used to overcome the force of attraction, and then it becomes solid, liquid, and then it becomes gas. And the reverse happens when you cool it, right? So I hope this is clear. Now in this state, you see, on heating solid it becomes liquid, and on heating liquid it becomes gas. On cooling gas it will become liquid, and cooling liquid will become solid. But what if I said you can skip the part in between and go straight to gas, right? That is sublimation and deposition. Okay, so what they want you to do is, they ask you to take a china dish and place ammonium chloride in it. Okay, ammonium chloride, and if you start heating it, it would directly become vapor, and if you cool it down, it would directly become solid. Okay, the process of converting solid directly into gas without even considering the liquid state, without even getting to liquid, it would directly convert into gas. That is the process that is called sublimation. And gas directly getting converted into solid, that is called deposition. Okay, these are the two terms. This ammonium chloride is one example where on heating this solid it would directly become fumes, directly become gas, and this gas on cooling it would directly become solid. There is no liquid in between. Okay, so this is sublimation, solid directly to gas, and deposition, gas directly to solid. And this is all that we have for this session. I hope you remember all these definitions. These are quite easy. If you have some doubts in it, please rewatch this video and get to know the definitions well. These are important questions that they'll definitely ask in exams, right? If you have any doubts, please put them in the comments. I'll get back to you as soon as possible. And also, if you have any suggestions, please let me know. Thank you so much for watching this video. See you in the next one. Bye for now.